Good morning, I'm Moreno and in this video I will present the work Improving Fairness using Vision Language-Driven Image Augmentation. This work tackles the important problem of bias mitigation on discriminative models. It is common knowledge that training sets contain biases which are then transferred to classification models via the training procedure. Thus, there is the need to prevent this behavior by introducing bias mitigation techniques. The fairness of the original training set can be improved by generating data with the intent to mitigate the bias represented in the training set. This can be achieved by applying generative models. Existing works train from scratch these models, which may be unfeasible and require domain-specific data. Thus, the main question of this work is, can we leverage pre-trained generative model instead? The setting of this study is the facial domain. Therefore, we have two main facial attributes to consider at the same time: the protected characteristic and the downstream classification attribute. We consider both in a binary fashion. The protected characteristic represents the attribute toward which the bias is studied, for example, age or skin color. The downstream classification attribute is the main task of the classifier, for example, big nose or big lips. Please note that this discriminative model does not know the protected characteristic at training time and at inference time. The key idea of this work is to balance the number of data points of a given protected characteristic in order to achieve higher fairness. The pipeline of the proposed approach starts with the bias training set. To make the explanation easier, we show here images of white people as the real bias dataset. The second step consists of applying the generative model to create a synthetic dataset which is then augmented. Another key idea of this work lies in the augmentation. Why is it needed? Well, because the generator is itself biased, consequently the synthetic dataset does not contain a high number of data points representing the minority groups. Thus, the raw sampling from the generated dataset does not allow to balance the original training set. We will now describe Vision Language Bias Control (VLBC), the proposed method of this study. This pipeline is composed of two modules: the synthetic image selection module and the augmentation module. We start with the real bias training set XR. Then a synthetic dataset is generated by exploiting the diffusion-based generative model DeFi. This dataset is then pseudo-labeled. This pseudo-labeling is needed since we require to know the protected attribute and the downstream classification attribute. Image selection is done by means of statistics computed on the training set XS. We compute the distribution of the generated images with respect to the protected characteristic and select images representing the majority class. These images will then be augmented toward the minority class in order to balance the original training set XR. Selecting images of the majority class gives us a greater and more diverse number of available images to be added to the training set XR. In the augmentation module, we make use of ContraClip, which exploits natural language to find meaningful paths lying in the semantic space of a given generative model. We apply this method to the diffusion-based generative model DeFi. The previously selected images are augmented toward the minority group. In this case, we make white people of darker skin tones, while keeping unaltered the downstream classification attribute. Finally, the augmented dataset XA is merged with the real dataset XR, balancing the original training set, making it fairer. The flexibility of this approach allows us to also increase the bias by augmenting towards the opposite direction. This is, however, discouraged, and we explore this direction for research purposes only. We run the proposed bias mitigation method across different downstream tasks of Sebe HQ, with age and skin color as protected characteristics. We capture the bias by difference in accuracy and disparity of opportunity, which is here indicated as fairness. The difference in accuracy is computed as the difference in the accuracies with respect to the protected characteristic classes. For example, we compute the accuracy difference of the model performing on white and black people. In this way, we capture how equally the model performs with respect to the protected characteristic. The ideal value of this metric is 0, where equality is reached. Experimental results in this setting show how the proposed method is always capable of mitigating biases across different settings while keeping high downstream accuracies. The performance of the VLBC is comparable to existing state-of-the-art works while maintaining consistent performance across multiple tasks, something that current state-of-the-art works lack. In the graphs, we represent the discriminative model training by increasingly adding 20% of the training set. The blue line represents the original data. The orange is the sampling from the synthetic dataset without applying any kind of augmentation, and the green and red lines represent the performance of the proposed bias mitigation method. We may see how the sampling does not work in circumstances where not enough images are available, such as in the case of skin color, proving the need to augment the images to achieve numerical stability. In contrast to existing works, the flexibility of the proposed pipeline allows us to increase biases by augmenting toward the majority protected group. This behavior may be required if specific augmentations are required. However, we note that applying this approach to socially sensitive protected attributes should be avoided. We may see how the proposed method is capable of increasing biases in four settings. VLBC Plus fails in specific scenarios where not enough images are available for augmentation. This is because here we are augmenting the minority protected group, such as black people, which is not enough represented in the synthetic dataset because the generator is itself biased. The graphs show the number of augmented images in red compared to the number of original images in blue in the failure cases. As we can see, there are not enough available images to be augmented to reach an equal number of samples. In this work, we presented vision language bias control, which leverages a pre-trained generative model to mitigate the bias of a given discriminative model, thus without requiring training. We make use of ContraClip, which exploits natural language to find meaningful paths lying in the semantic space of a given generative model. Those paths are used to augment synthetic images toward the minority groups, allowing to increase the fairness of a given real training set. The proposed method shows competitive results against state-of-the-art methods and shows consistent performance across multiple tasks, something that current state-of-the-art works lack. Finally, the proposed pipeline can be applied in the opposite direction in order to increase the bias. This is done by augmenting toward the majority group. Thank you for your attention.